So at the end of last lecture, I indicated that that the construction of cohomological induction, one reason to do it certainly is that it gives cohomological representations. So my plan was originally to introduce these again and go through the proof that the construction mentioned last time, or the AQ lambdas, exhaust the list. But actually that's not going to be possible, I think. Certainly not the details, because it's quite tricky. So I'll just make some general sketch of things and then odds and ends, since this is my last lecture. Okay, so recall that from last time, or well, not recall from last time, but what is, let me say what GK cohomology is again. Okay. So this is simply on, the category of derived, the way I put it last time. So if one goes to, okay, so if you recall, just to be pedantic, the forgetful functor from GK modules to this thing given by taking invariants. So that is maps GK modulo homomorphisms from the trivial representation to V. This is GK invariance, the GK invariance in V. This, the derived functor is GK code. Okay, so this is for I. So, but of course now, this is a little abstract definition. I'll just repeat, just briefly, the definition that many of you will have seen before. So this is an explicit definition using complexes. Okay, so one takes the, so just as a side remark, there's also the functor which was the, so this was an I functor. There was also a P functor like this, and that gives homology. Okay. In any case, for most of the modules we're interested in, the duality theorem, which was mentioned last time, more or less says that homology and cohomology are the same, so we sort of will ignore that. Yeah. And anyway, it's less interesting. Okay, so the explicit definition uses this standard complex, so I'll just write this down quickly and then go from there. So CGKV is defined to be the Horms, the K equivariant Horms from, so the notation is all the standard notation, I'm not going to repeat it. Okay. And there's a differential from CK to CK plus 1 defined by a formula which, for those who have seen it, this is usually the first definition which is given. Okay, so basically the differential has two pieces. One just takes your K cocycle and you apply it to the K tuple you get by omitting one of these, and then that one is used to then apply on the module. This is under V, and the other one is just that you remove two of them and take the bracket and put it in the first place, and you have to take in these signs. Okay. So this, I mentioned last time that there are post-full resolutions which compute the functors in generality. This is what you get from that standard resolution. Okay, but okay, it's a derived functor also. Okay, so we are interested in. So let's say that we write this. We are interested in GK. Irreducible unitary GK modules. So I should say unitarizable, but it doesn't matter. So I'll just, by results that have already been mentioned, such that So G, of course, for me is a connected real algebraic group always. So I can take its complex points and I take a finite dimensional representation, which is given by the Cartan-Pyle theory. And we are interested in the irreducible unitary GK modules, for which this cohomology functor is non-vanishing on V tensor E dual. Okay, so this is the contragradient, which maybe last time I denoted EC, but others E star. Okay, so why I will come to the end of the lecture. So in some sense, actually, my whole series of lectures has been in reverse, in the reverse of the natural order. I should have started with the motivation, but that will come in the end. Okay, so there are some simple remarks to be made. Let me just make a state. Okay, so there is one basic thing, very basic thing. This is known as Wigner's lemma. So irreducible unitary GK modules have an infinitesimal character. Yeah, that's right. So if chi v, chi w are equal to the infinitesimal characters in the maximal spectrum of C of G, then xi, okay, so let me put it this way, hi of gk v tensor w is equal to 0 if, let me make w star, if chi v does not match chi w. Okay. Okay, so this is 0 in all cases. Okay, so I'll just give a quasi proof maybe. Yeah. So by more or less what we have said about the category of GK modules, maybe this is an amusing exercise. This is the same thing as the X in the category of GK modules of W with V. Okay, so if you haven't seen this before, think about why this is true. And now a very general argument tells you that this is 0 if chi v is that. Just to say why, if in particular okay, so this is a standard argument that if you slightly modified, if you have a ring R and you're looking at modules of X between two modules of R, and the center of R, or any ring, any element in the center of R, can be made to act by different scalars. When I say scalars, I'm assuming R is a C algebra, but if you can make it act by different scalars, you can make Z act by 1 here and 0 here. And it's a simple exercise which people from in homological algebra to say that can't happen. The only way that can happen is
you would adopt the extent of
Wigner's lemma it's like Xerox, it's a generic word. It can be used in any context.
Sorry?
Wigner's lemma is like Xerox. Once it was somebody's name, but now it can be used generically in any context.
Yeah, it's the first time I've seen this and somebody using it in this generality.
Yeah.
It's in seminar sophistry in a talk by Kante.
So that's probably before Wigner.
Huh?
That's probably much before Wigner.
Yeah. Wigner is not the physicist.
The sun Wigner, yeah. So then therefore that it must be it's definitely before Wigner.
I don't see why this is not related to.
Okay, so I'll put some quotes.
I think this mistake, Borel is responsible.
Okay.
This is definitely before
Borel,
it's before that because like somebody else's.
so it is seminar certainly.
Sure.
That shows that this is always.
No, he was not a physicist. He is a mathematician.
Oh, he's not a
Okay, I should say that in the rest of the talk I will call these cohomological representations. I don't want to keep saying irreducible unitary cohomological representations, I just say call this cohomological representation. That is irreducible unitary GK module with that. Okay, so immediately we know something from here, that's right. So this tells us that applying the lemma that V must share the same infinitesimal character, the same
incomplete very particularly it's exactly like the Lie algebra homologic.
Sorry, it is the relative Lie algebra cohomology. Yeah, this is called the relative Lie algebra. Okay, I don't know where it. Okay. So
K is zero. K is zero, that's exactly.
yeah, if K is trivial, if the group K is trivial and the Lie algebra K is 0, then this is I guess that Cartan-Eilenberg, is that okay? That first appeared in Cartan-Eilenberg, I think. Okay.
Yeah, but the Cartan
Of course,
came after the superficial.
Okay. So all names should have quotes around it. Okay. So, so this has the same infinitesimal character as E, and I guess it has been sort of indicated, but maybe not said explicitly, that the infinitesimal character of E of a finite dimensional representation is lambda E plus rho. Okay. So what does that mean? Remember that infinitesimal characters are measured inside, are taken inside the space Cartan modulo W, modulo the Weilbrook pattern. So you choose, when I talk about highest weight, so lambda E equals to highest weight of E. Okay? So when I say highest weight, it means I've chosen a Borel, and once I've chosen a Borel containing this Cartan, then there is a notion of rho, which is the half sum of roots appearing in the Borel, and there's a notion of highest weight, and this object can be thought of inside here. And anyway, it's only defined up to W. Okay? But that is the infinitesimal character. So notice that this is always regular. So as Raghunathan in his lectures, we saw that this is in the dominant cone, the closed dominant cone. But adding rho makes it regular, meaning it doesn't lie on the walls of the closed dominant cone. Okay. So we have already reduced, by looking at these representations, we've reduced ourselves to certain special representations. Okay, the other point is, of course, that we saw that the finiteness theorem tells us that once we fixed E, there are anyway only finitely many of these, because, for example, they all have this infinitesimal character. Okay? So we're trying to understand a finite list of representations. Okay. The second remark I want to make is that, which I'll just put here to make things more messy, which is that if theta is the Cartan involution corresponding to K involution, then for this to happen, then the infinitesimal character of a unitary representation is invariant under theta. So it follows that the infinitesimal character of E must be theta E or theta chi E. Okay, so this is chi. That's consistent. Okay, so that's just a remark. So we're only now in the discrete series case, that is the rank G is the rank K. This will not really be a restriction. All coefficient systems will be allowed, but in other situations, it does restrict which coefficient systems can have irreducible unitary GK representations of that property. Okay, so then the theorem is that the homological representations in this sense, right? So irreducible unitary GK modules such that that is 0 are exactly the AQ lambda. So last time we used this notation RS C lambda, constructed by, given by a pair consisting of Q, which is a theta stable parabolic, and then one has associated with that the Levy, etc., and L, and lambda is, okay, I'll take it to be a unitary character of L. Okay, one-dimensional unitary, unitary character of L, one-dimensional. So I guess this is the pair. Okay, and when I say exactly, that's a bit not good language, maybe. Okay. So because there are redundancies in this parameterization, yeah. That is, it's possible for two different AQ lambdas, AQ and AQ prime, to give the same irreducible GK. Okay, so this is the basic theorem, and this was appears in the paper of Bogan and Zakulan from 1984, and there are, I'll mention what the elements are in this. So last time I at least stated the theorems that tell us that this is irreducible. Oh, sorry, unity character satisfying positivity condition. So I'll rewrite what the good condition was. The good condition was that lambda, lambda plus rho alpha is greater than 0 for all alpha appearing in new Q. Okay, so Q has a Levy decomposition. Okay, and for every root space of, I'm assuming that, okay, so when I write this, I'm assuming I fix my Cartan and I'm looking at roots with respect to that Cartan, and the roots appearing in U must be, lambda plus rho must be positive, lambda plus rho mu must be positive with respect to that. Okay? So recall that this was the infinitesimal character, this is chi of this module. Okay. Okay, so if you recall last time, there was a weekly.
Capital S.
Yeah, S is the special dimension, so that was dimension of U intersected with K. Okay, so under the good condition, these functors R, J, C, lambda vanished in all other degrees. This was the only degree in which they could be non-vanishing. They agreed with the L functors, and they were irreducible and unitary. Okay. So the proof of irreducibility, I mean, since you asked yesterday about proofs of irreducibility. So the proof of irreducibility consists of understanding, well, I mean, there is something called there is an easy way to identify a certain submodule of anything, which is called the bottom layer, okay, which is doing a compact version of the cohomological induction. And that contains certain K types, which the analysis of, there's one particular K type, the analysis of that K type allows you to eventually prove irreducibility. But it's very complicated. Yeah. It's not straight, simple anymore. Unitarity, I won't say anything about it. Okay, so just to say that, right, okay. Okay, so I hardly be able to say much about what goes into the proof of this because it's somewhat takes time. But let's at least understand what this says in some instance. Okay? So there's an example which is SL2R. So last time I stated, at least showed you one theta stable parabolic for GL2. Oh, okay, so I should say that there's one question here you might ask. So we know that this lambda is the infinitesimal character of the lambda. So for a given E, if you're starting out with an E and you want to list the finitely many things, then what you have to do is you have to just match this guy with that guy. Okay? And of course you have to match them in H star mod W. Okay? So in fact if you just, yeah. Okay. So that's what the lambda is fixed according to that. So in SL2R, so the point of this is that it reduces the classification of these representations and computing many things with them to understanding the theta stable parabolics and enumerating them, and that's easy, right? Okay, so maybe I'll just say the general thing because I said it last time and then give some examples. So to enumerate, so therefore, to enumerate theta stable parabolics, enumerate cohomological representations. One has only to enumerate Q's. Okay, and for this, there's a standard recipe. So you start with, you take a theta stable Cartan. So let's, I'll take it in the real group. Let's write it as T0 plus A0, where T0 is the part where theta acts by 1, and this is the part where theta acts by minus 1. Theta is of course the Cartan involution. Then one knows that, I think this has appeared in several lectures, that the real roots, the roots alpha in the root system of HG are real on IT naught, square root minus 1 T naught plus A naught. Okay, so fix an element of IT naught and define here Q of say lambda naught, which is L of lambda naught plus U of lambda naught, and L of lambda naught is the sum of the root spaces on which are positive on 0 on this thing, and these are root spaces which are negative or positive. Okay, so this is L and this is U. Right. Okay. So okay, and if you, it's immediate that the complex, the real, with respect to the real form conjugate of Q naught is L naught plus U bar of L naught, which is U of U bar, which is the same thing plus that. Okay. So this is just an, all these are just exercises in elementary linear. Okay. So I should have said, of course, that the theta stable Cartan is unique up to add k conjugacy. So conjugacy of the adjoint group of k, I'm maybe assuming everything is connected, so let me assume that. And therefore, up to add k conjugacy, up to add k conjugacy, up to add k, every q theta stable is of this form. Okay. So now let me do the example. So SL2R. So we have a complete listing of irreducible admissibles, at least unitary, up to infinitesimal equivalence from Professor Narayan's lectures. So let's see where this sits with us. So so there are three theta stable parabolics. Let me call them Q plus, Q minus, and G. G itself is of course theta stable. So G is not terribly interesting, the other two are the important ones. And one can realize Q plus as the Q of the following element, which appeared last time. And Q minus as the okay, I think I put this right here. Okay. Okay. And okay, so these two lead. Okay, so the modules you get AQ plus. Okay, so there is one more point. So I have to fix. Okay, so let me just discuss this one. I have to fix a. What else do I have to fix? I have to fix my Q, and I have to fix a unitary character of the levy. So last time I indicated that the levy here is actually GLNC in the general case. In this case, it's just C star. Okay, and actually it's not C star. It's A B minus B A, but with the condition trace is 0. Right? Okay, so this is the levy. Okay, so one has to fix a unitary character. Okay, so maybe I'll leave this as an exercise. Run out of time otherwise. So check. Okay, so let me just say what the statement is. So AQ plus of lambda for suitable lambda gives me back the discrete series dn plus. AQ minus for suitable lambda gives me back the discrete series dn minus. Okay. So if you specialize this to the functions for these two cases, and G gives you the trivial representation. So it's just a positively condition on basically, but you see the point is that it's you could put the condition that this was true for all groups. It's weaker than that. It's only the true for roots in U. Okay.
Something like bringing everything down to the cost of the dominant chain of U.
Yeah. Well, that's dominant chain of U maybe that makes sense. Okay. So one remark here is that I'll say something about proof of this theorem. So one remark here is that if lambda naught is regular, so lambda naught is taken IT naught. Okay. So it's, I guess it's a slightly non-obvious fact. Yeah, maybe it's not an obvious fact that T naught. So in my general setup, T naught is part of A naught, H naught, right? And it's a fact that T naught contains elements which are regular in H naught. Okay, so let's accept that. So if you take a regular element, then obviously what you're going to get is a Borel sum. Okay, it will define a positive system. So if lambda naught is regular, then you get a Borel, theta stable Borel subalgebra. Okay, and more or less that's the only way you can get a theta stable Borel subalgebra. Okay. So let me just make a write this down. Yeah, maybe I have one more. One can say more, I didn't say this theorem statement is fine, there's no problem with that. But there is one remark that can be made maybe. The one-dimensional character is realized. So this will come out. I'll give a sort of proof of at least that they are cohomological, and then this fact will become clear. Is realized in EU. Okay. So in fact, to be cohomological, you'll see an irreducible that EU. This is the things killed by elements of U, right? Vectors killed by elements of U. Has to be one-dimensional, and it will actually be the character. This is obviously a representation of L, and it is actually the character that you want to induce, cohomologically induce. So you write it as RS. See that? I'm just telling you how you normalize going from E to lambda. Okay. So it follows that therefore, if dimension so if highest weight of E is regular, then this only happens for U equal to for Q equal to a Borel. Okay. So if your finite dimensional representation has regular highest weight, then the only parabolic subalgebra for which EU will be one-dimensional will be actually a Borel subalgebra. Yeah, and so this implies that under this condition on the regularity, the only AQ lambdas relevant to the theorem are discrete series. So last time I think I stated this, but it's a fact maybe, that the Q equal to Borel modules are the discrete series, so or fundamental series. I mean, I haven't assumed I have this, but okay. So I didn't say this last time, but okay, maybe I'm not sure. So to get after all we
There is a small point that if Q contains an ideal,
Yeah.
which is completely retained in K.
Yeah, then it's also
Yeah.
true. That's right. Yeah, up to K. Thank you. So the Q equal to Borel modules or up to K. Okay, up to an ideal in K. So it's true that if Q is a Borel subalgebra, you get the discrete or fundamental series, but there are some more things for which you get the discrete or fundamental series. Nevertheless, this remark is stated as true is that if lambda is regular, then the only AQ lambda relevant to you are discrete series. However, those discrete series will may appear in another way also. So, as I said, this is an example that the parameterization is redundant. Yeah, there are different AQs can be isomorphic. In particular, as Arsati pointed out, if the Q and Q prime differ in something which is contained in K, then they will kind of give the same one. Okay, so the induction doesn't do anything. Okay, that's what I want to say. Okay, so maybe this example shows you that these are actually very simple representations. I suppose already it was remarked that in the case of SL2R, at least the Casimir eigenvalue, which is of course included as the central part of the central character, the Casimir eigenvalue already separates the discrete series and the trivial discrete series at least from all the principal series and the complementary series. So in some sense, the fact that these representations are only the simplest ones in the case of SL2, just one could see directly. Okay. Maybe I should briefly say in SL2, okay, because I think this picture was mentioned. Okay, I am almost sure to say something slightly off, but let me try. So, in SL2, if you take the full induced, then we saw that the picture is that the K types are all one-dimensional. See, these are K types, right? They're all one-dimensional, they are all the same parity, and they are two apart. So I have operators going from K to K plus 2, and then this way, and that way. Okay? And I think we saw the picture that when you have somewhere a finite dimensional representation, and then you have the remainder is two things which are actually the discrete series. Okay, so I'll just call this dn plus and dn minus, not worrying about what the n and k are, how they're related. Okay, well, I mean, this is the lowest weight is n that appears here, and this is. So, just as a remark, this shows you why the discrete series has cohomology, because I can always take the module, I can just quotient this by this module. Okay, so now I'm left with this part of the module. And this module is easily seen to be an extension, an x1 of the finite dimensional module with the discrete series. And that is, as we saw, x and cohomology are the same thing, right? So I should have said here, as a consequence of this is also equal to x I gk of trivial and c. Okay. In general, this cohomology is the same as x I gk by that same remark that I made before of E with E. And x1 is extensions, so this is an extension. And if you look at it, it's easy to check using the GK plotting structure. That's a non-split extension. That's not a trivial extension. And for dn minus, you just quotient by this guy, right? And it produces, you quotient by this submodule, right? And that provides an explicit cohomology extension of dn minus with this finite dimensional representation, and that is the cohomology again. Okay. So everything is fairly.
When you are defining the AQ plus lambda, so that lambda becomes from the I n.
No, see, you have to match. See, what you have to do, you have to just by Wigner's lemma, You have to match the infinitesimal character with the infinitesimal character of that. So that's, you have to match lambda plus rho u equal to lambda e plus rho, but the w opens. Yeah, so if you just try to solve this equation, the obvious solutions are there and they turn out to be all right? Anyway, the point is that once you have the theorem, you just have to adjust. See, the q is a fixed thing, lambda varies. So once you have a q, you can fix lambda. You may or may not be able to solve the equation. So that lambda irregular is a case where you cannot solve this equation for q which is not Gödel. That's what the content of that remark is. Okay? Maybe I'm saying things in a very complicated fashion, but yeah. Okay, so these are the what time did I start?
45.
Oh, okay, so very quick proof of the existence of homological representations. So there is a spectral sequence. So maybe this is not a good idea to say this even, but there is a spectral sequence which has the following form. I mean, and this comes out of all the formalism quite easily, of course. So for a given V and W, there is such a spectral sequence, top exterior power of U, okay, and it converges to, yeah, so this is slightly, there's one technical point in this. Sorry, so I take this to be a finite dimensional representation, which is my coefficient system, right? X, E, R, Q, S of okay, so let me just remark what this is. So this spectral sequence works only under those conditions, in the sense that when that unitarity, when the goodness condition happens, so that this is in a single degree, which is S, then you have such a spectral sequence. Now, I'm not going to say anything more about it. It just comes from Frobenius reciprocity and some playing around. From general principles, one knows that, of course, by this Wigner lemma, one knows one has to match these two characters here. Not just infinitesimal character, but the character of A sitting, a certain torus sitting inside there. Okay? Okay, so I won't go into it too much. And this degenerates, and one ends up with the following. Okay, so maybe this was not okay. Okay, so this implies that the X of E to H star so there is an argument which is elementary, which boils down to the following. The GK cohomology, which is just after all the X of this type, we just said that, turns out to be the cohomology with a certain shift, which is the dimension of U intersected P, of L, and the compact support L, the compact part of L. And this module is the C lambda that you're choosing to induce, and this module is the EU, okay? The invariance under U contributing. So basically now this vanishes unless these two match. And when these two match, then it's just the compact dual. It's just the cohomology with a shift of this kind, of the trivial ring. So these are all explicitly computable. Okay, so I won't say any more about this because I have other things. But this it's from this just elementary analysis of the spectral sequence that you get that. Okay, so I emphasize I have
Constants theorem from there.
You don't need quite Constant's theorem because you see this is the top, well maybe, but certainly this, to match the top exterior power of U and this thing, it can only happen when Q is in the top degree. So you basically need to know the top degree. that this character doesn't appear in any of the lesser degrees, but that is, yeah, it's certainly given by Costin's theorem, but maybe you can get away with less, maybe not. You basically need to say that these only match with that. Okay, so the point I want to emphasize, but I haven't computed enough examples, is that the theorem is explicit and it tells you how to compute stuff, and it's very concrete. Okay, or the result is it. The other point is that you can compute with these things, and this degeneracy, which is where you get the same representation multiply, is related to something called Arthur packets and the parameterization of Arthur packets. And it actually allows you to make computations about Arthur packets quite easy, which is kind of fun. So let me make some remarks. Okay, so this will be very quick remarks. So I consider that we have justified that these are cohomological representations, which is maybe not the. So I should have said that all discrete series are cohomological. I showed it to you for SL2 by picture, but it's always true, right? Okay, so in this theorem, the construction is, of course, I've given the construction using Zuckerman functors, but Parsati gave a different construction first. And unitarity, I just quoted this theorem, and in general, unitarity was first proved by Hogan. And so then the remaining part is exhaustion. Okay, so that is, how do you know you've constructed all of them? And this is the heart of the thing, and there are two ingredients. This is what's done in the Hogan-Zuckerman paper. There are two ingredients which I'll just say what they are. So, okay, I'm going to abbreviate this. This is called Parsati's Dirac operator inequality. Okay, and it's an inequality with the following sort of. Okay, I won't say more about it. Okay, so it basically, for unitary representations, it sort of bounds the k-types in terms of the eigenvalue of Casimir. Okay, so this stands for Parsati's Dirac operator inequality. Sorry. And the second thing is the theorem of commutation, which, okay, so at least let me say why this is relevant. So we've seen that I forgot to say that part. Okay, so we've seen that the complex computing cohomology is something like this. So we can actually put P star here for the Cartan, this P for the Cartan state. And here I have pi or V tens or E tens. V tens and E. Okay? Let me just assume E is trivial. Okay, so something, well, basically Wigner's lemma, a slightly different version of it for unitary representation. So, generally goes by the name of Kuga's formula. Actually tells us that the GK cohomology of V will be the Hom from exterior IP into the zero eigenspace for the Casimir. Okay, and commutation, I guess this was suggested to you by Parsati, but commutation found that there is a very special k-type. So, special k-type in exterior IP star for a given unitary cohomological representation. So the point is that the Dirac operator inequality, so you assume that the Casimir is 0. So that part goes out of it. So it basically tells you about the weights appearing, the k-types appearing in such a representation, in a unitary representation with 0 Casimir. And the basic idea is that there is a special k-type here which can more or less determines this, the rest of the representation. Okay, so that is commutation theory. So this is that's the two-line bullet point summary. But the arguments are somewhat intricate, but and somewhat tricky. But then they go into all kinds of arguments about roots and weights. But that's it. So the combination of these three, all these results shows that you have this thing.
HI is one-dimensional.
HI is not necessarily one-dimensional. No.
In fact, k-type approximately, and also V is approximately, and
so that k-type is in the lowest degree, in the degree, in the bottom degree of this guy. That's the sort of strongly primitive K-type. In general, HI is not 0, but in the lowest degree in which it appears, it's one-dimensional, and then other stuff appears. I mean, the first time it occurs neatly. I think that's the only time it occurs. Is that right? The strongly primitive K-type doesn't occur again. Oh,
What is the question?
so the K-type appearing, the commeration, the K-type isolated by commeration, it appears, it contributes to the, it's related to cohomology in the lowest degree, right? It's this, I mean, this is the thing, right? That's the only, it only appears in that degree. Yeah, it doesn't get repeated.
So it appears and it appears in complexity 1 there.
Yes.
Also in V it appears in complexity 1.
And then it determines B, basically. Determines the rest of
That is one and
in that degree, yes.
that.
In only in that degree. But it determines the K-type structure of it. Okay, so I mean, this is, anyway. Okay. So, since I have about 10 minutes left, and I don't plan to give any more details about the argument, but I insist that, I emphasize that these are, the theorem reduces these to nice computable objects with which one can play. Okay. So, I think just to emphasize the relevance of these representations to the rest of what has been talked about, I'll just quickly recall why these are interesting. Why these are interesting. Okay, so let's now take a situation where G is over Q. Okay, and M is the quotient of GR, modulo its maximum compact, modulo common arithmetic subgroup, or let's say any arithmetic subgroup.
Can you reach it? That very equal to this one.
This one? This one.
Okay. Oh, yeah.
HIGKV is equal to the Hom K exterior IP to the zero eigenspace in V of the Casimir.
Yeah, there will be some K invariant and exterior P. Will be multiplied by
Sorry, right. The strongly primitive, sorry, that's true. Yeah, you're right, yeah. I mean, this may not be in a single degree, sorry. So, the trivial K type can be allowed to generate. In fact, that will exactly generate this thing. I mean, that's not equal to that, but to the copy, it will be the modulo to that. Yeah, sorry, okay, so well, we can also jazz up things by looking at finite dimensional representation.
Casimir is operating by trivial on all of V. Why do you put V0?
Sorry?
Casimir is operating trivially on
There's
all
no
of V.
reason to do that, you're right. Yeah, because I had originally written this for C infinity G, but for an irreducible, anyway we have a single infinitesimal character, so I can ignore that. So the point is this holds in, okay, fine, yeah.
The second is true. Yeah. Whatever will test operates, that's it. The result is correct.
No, only when Casimir operates trivially.
It's equal to the cohomology.
All components vanish anyway.
Otherwise all cohomologies vanish anyway by Wigner's number. That's assuming V has.
Statement you made is correct.
No, but I didn't specify what V is.
How is non-zero?
What will not? Oh,
How is non-zero but homology is zero?
Casimir is not to take that account.
Yes.
Okay.
Yeah.
This statement is
Okay,
true only for
sorry.
Casimir operation.
So now I've already assumed that the Casimir is operating trivially, but I could have, I didn't specify V. I could have put L2G here and L2G0. That would be a unitary representation. Then I need to first restrict to the 0 of the Casimir. Yeah. So let me just put this for, it's redundant, but nevertheless. Okay, so this is this thing. So I just want to relate it to Matsushima's formula and all that. So if you have a finite dimensional representation on EC, then one has a module as the same kind of induced construction that we did before, and this is a vector bundle with flat connection or a local system, or what Dragan called an integrable connection or equivalent to, and on M. Okay, and then the classical Matsushima formula says that, or some formula or the other. So, okay, let me just write down what it is. So I'll just write down a series of equalities. Okay, so this is, some of you may see this as Matsushima's formula. I'm assuming that this is compact. Let's say M is compact. Okay, so if you are not familiar with cohomology valued in local systems, just think of the trivial representation. So then it's just the cohomology of this G mod K mod term. So the first step is completely elementary. The second step is a little more complicated. So I'll just say that one replaces this with L2, and then one uses the discrete decomposability of L2, which was mentioned in Ravi's talk. And one has to show that that Hilbert space direct sum decomposition of L2 passes through an algebraic, this is an algebraic finite direct sum. It's already finite because remember we have to match the infinitesimal character. So Harrison is fine. Of things like this. And the point is that now these spaces are completely understood thanks to this theory. I mean, it's maybe a little this thing to say they're completely understood. But so the point is that that's why they are of relevance to G mod gamma and automorphic forms. And one gets a lot of information out of this. For example, one gets the following vanishing theorem. This is maybe not the best possible. Well, we already have a vanishing theorem because of that observation. When Q is a Borel, and let's assume we're in a discrete series case, the discrete series guys only have cohomology in the dimension, the middle dimension, that is dimension of G by K by 2. So that means that everything actually vanishes up to degree G by K over 2. Okay? I mean, this is not G mod K over 2 if G has discrete series and lambda E is regular. But more generally, this always vanishes below the real rank. Okay, and this follows from a little bit more analysis simply because these vector spaces vanish. Okay. So the point is that just knowing what the Archimedean component of an automorphic representation, after all those are the things appearing in, so let me just write here L2. In L2 of that thing. If you wanted to contribute to the cohomology, then automatically there are strong restrictions thanks to this theorem, and you can say a lot. Of course, that part is extremely subtle. Them down. Okay, so that is all I wanted to say about these matters. I just wanted to finish with some remark about odds and ends, maybe. Since I spent a lot of time on cohomological induction, I want to justify it somehow. So maybe remark one, this is unrelated to what has gone before, is that, so recall that we were doing the following thing. We take RQS C lambda, and when lambda is good, we get the cohomological representations. And when lambda is weakly good, we still get something. We get irreducibles, but maybe zero. Irreducible and unitary, because that theorem also applies. So that means that if you take Q to be the Borels, Borel, and the family of Borels, this gives the corresponding representation is the limit of the discrete series. I'm assuming here that G has discrete series. Otherwise, you get some kind of interesting representation, which is the limit of the fundamental series. Okay. So the point is that the cohomological induction, I think, was the first way that these limits were defined as representations, and a complete understanding of their non-zero-ness and irreducibility was available. So I'll just remark to make a link with what sometimes appeared in Milicic's talk, is that there is, he mentioned that you could translate, in the D-module picture it's easy to see, you can translate lambda to a wall, so to speak. So if you recall, good and weakly good basically is a condition that something either lies in a certain cone or it lies weakly good as it lies on the edge of the cone. And something which has not been discussed but are these translation formulas of Zuckerman. And essentially you get this representation from a nice discrete series representation by translating. And so the cohomological induction formulas behave nicely with respect to translations. Okay? And this gives you, and as we saw, it was mentioned there that the translations are either irreducible or zero. And that fits with this theorem nicely. I'm just remarking that. Okay? This was one remark. The second remark I was going to, I think I have time. Second remark is the relation with the D-module picture. So I'll just say it very briefly. So the discrete, so the cohomological representations from our point of view, they are nice representations singled out by this cohomology dimension relation. And you know, they're the best of all possible representations. Right? So there's a discrete series or trivial or very nice simple representations comparatively. Right? I mean, they're really good. And as I indicated here, they are, at least at the present, they're the ones that are most directly related to automorphic forms and arithmetic geometry through this relation. Right? On the other hand, it would be not surprising that from the D-module picture also they are quite nice. So I'll just say what that thing is. So suppose you have Q. This corresponds to a complex parabolic in G mod C, and let's say I choose B inside Q, and then I look at this map from the flag variety to G mod Q, and here there are closed KC orbits. So KC acts over here. So I'm writing KC because my Q is always compact, but when it's natural in the geometry picture to look at complexification. And this has closed orbits. And let's say I have a closed orbit, let me call it C. And I can just pull it back to G mod B and get a closed thing here. This is not necessarily a single orbit, but it's a sort of closure of one orbit. So pi inverse C is the closure of a single orbit. And this is a miraculous fact, is smooth. Okay. So the point is that it's a smooth orbit, unlike your generic orbit in G mod B. And then the geometric data that was mentioned in Dragon's talk, geometric data. Okay, so let me call this Q, curly Q and tau, which I'll leave unspecified for the moment. But so this geometric data classifies is the data corresponds to AQ lambda. Okay, so for the appropriate relation of tau to lambda. Okay? Remember, everything anyway is always fixed. All these parameters tau, lambda are just fixed by requiring your infinitesimal character. And so there's only one way to solve both, not to W. And so these orbits are the orbits of this thing. I hope I'm saying this right. And this again gives another parameterization of these representations, because with a little work one can say that the closed orbits of Kc and K mod Q are in bijection with W mod WL mod W K. Depending on which side you write. Okay? And so one immediately comes up with, in the geometric picture, one immediately has families of representations or packets of representations which have this cardinality. Yeah, or which are like in bijection with this coset space. And that's the geometric picture. So the only thing so I'm not sure if one could, okay, so I'm done, but I'm not sure if one could classify, reprove all these theorems again, but it might not be interesting also. And the point is, unitarity is not built into the geometric picture. Okay, so this is all I had to say.
Thank you.